get started. Okay, yeah, so as always, folks offsite, tell me if you can't hear clearly. You know, weeks 1 and 2, basic stats. Weeks 3 and 4, kind of trying to reinforce how to do mixed effects models with a time series example. And then week 5, we're kind of pivoting into doing spatial models. And, you know, so far, the time series models, we started out with discrete time, so kind of, you know, doing these kind of projecting equations from year t to t+1. Whereas for spatial models, we'll, this week and next week, when we get into 2D space, we'll start out with evenly spaced locations, but we'll want to get to the point where we can choose any locations within a domain. So that's sort of what we're trying to do with the lab here, as well as solidify concepts about spatial models and keep talking about separability. So, okay, my never-ending use of the California Bite cartoon I did one sad morning, where we have 8 different locations, and you know, in my experience, a lot of times, you know, biological sampling programs that people aren't developed by statisticians end up looking like this, where people kind of implicitly ended up doing sort of like a space filling strategy, where they pick locations that are sort of biologically interesting or close to their homes or close to universities, but also spread out across space. So what, you know, are there any kind of, you know, what if somebody gives you data where you have a bunch of locations that, and nobody tells you how they selected those locations, and they're kind of spread out evenly, kind of, you know, like this, can people think of kind of pros or cons of that sort of implicit space filling design?
Helps if they're spread evenly, right? If it's like a grid pattern.
Yeah, so then why does it help?
Because you have more regular sampling at like specific spatial intervals, and so if you're trying to interpolate between locations, you have like a regular grid distance.
Yeah, well, so I mean, the models we'll talk about can extend to irregular distances, but I think that one thing I'm hearing you say is that you can interpolate. There's maybe benefits to interpolating if you have evenly spaced points. So under sort of like a Bayesian optimal sampling design, a lot of times this sort of space filling approach is optimal under some scenarios where, you know, to minimize predictive variance, you want to have sort of the whole area covered. So anyway, and what are the downsides maybe of sort of a space filling approach?
Cost money.
Cost money, that's a good one. Yeah, travel time usually costs.
You don't get, it's harder to get a measure of sort of real small scale variation.
Totally, yeah, so.
Can you share the screen?
Oh yeah, the screen share.
It can also be hard to get to certain locations. Like
Yeah.
if you want to stay on a specific grid.
Totally.
This would be more of a problem on land, but like
Yeah.
if your location's on the edge of a cliff.
Yeah, so right, so doing like too strict of a fixation design, you end up with kind of infeasible, kind of way infeasible locations being selected. It costs more, and then John's point, you know, like I don't think I have scheduled anywhere to talk about sort of spectral analysis. Has anybody looked at wavelets or Fourier transformations or? Yeah, so the claim of time series stuff, and it extends to space, is that if you've got a white noise time series, that it has equal power across a uniform set of frequencies, and so the power or the variance associated with fine scale, you know, with small scale correlated process, and broad scale correlated process is about equal in a white noise or high ID process. And so, a lot of biological processes have a spectrum associated with them. How much power is how much variance occurs at the scale of, if we're talking about time series, how much variance occurs at a second scale or a day's scale or a year scale or a decadal scale. Oftentimes a biological process has a characteristic power frequency function. And so if you have even space, you're only able to pick up on the frequency that's approximately equal to the distance between locations, and you're losing any ability to pick up on spatial variation at a scale smaller than about the distance between your locations. So just to talk more about that a little bit, like what are the spatial processes, like what, if you have if this was the California Bight, so we've got, Point Conception out to the west and the border of Mexico to the east. You know this area better than I do.
Close enough.
Close enough. I don't really know geography. Well, it doesn't matter. I'm moving up to Alaska, so I can forget the very little I've managed to learn about California. What are the sort of like biological processes that might cause things to be varying? What are the different biological processes that cause spatial correlations? Spatial correlations in rockfish density or fish density or kelp or whatever you want to talk about.
Environmental similarities?
Yeah, so environmental similarities like water temperature, say, might be correlated, and like oceanographers would say that water temperatures might be correlated at the approximate scale of an eddy, which might be these oceanographic eddies that get set up, that might be a, mesoscale, whatever that means, like 10 to 100 miles. And there's streamers where they like go on offshore, and there's a bunch of ocean temperature stuff that's occurring at the scale of 10 to 100 miles, say. Like what other processes are occurring? Upwelling, yeah, which might be occurring totally synchronized coastwide due to Ekman transport and broad scale stuff. What other stuff is happening for rockfish densities?
Geology, bottom structure.
Yeah, so bottom structure is going to be driving like kelp settlement or not settlement, and that probably varies, on the scale of 100 meters, like different like beach, like if sand is over rocks, kelp can't deposit there, and sand placement along the bottom is occurring at about the beach, beach cell, like beaches have like a transport cell that's set up due to local conditions that deposits sand during tides and during storms. And so there's, like kelp densities are occurring at maybe 100-meter scale. There's also like just fish are distributing vertically at the scale of 1 to 10 meters, based on predator refugia, So there's a bunch of biology that's occurring at basically any scale you could look at. And that'll result in some power frequency for spatial correlations between these sites. And if you have a space filling strategy, you're unable to distinguish kind of fine scale processes, at a smaller scale than the average distance between locations.
So if you have a grid format, you're missing some of the smaller scale issues. But if you have two stations that are very, very close together, the things happening at the fine scale there probably don't apply to other areas.
Yeah, but it could still be useful to partition, like to at least work out how much, my claim is that it can be useful to sample really fine scale locations to figure out how quickly things decorrelate, like what proportion of variance decorrelates really quickly versus very slowly.
Okay.
If you use a parametric correlation function, usually it will just estimate the dominant mode of spatial correlations, and I don't really want to get into the details of it too much. But every one of our parametric correlation functions has a parametric power frequency function. And typically it'll just pick up some portion of the empirical power frequency function. So this is getting pretty far into sort of some weeds, but I just thought it'd be fun to talk about. Spatial sampling designs for a second here. So if you analyze it, blocking, like, where you assign sites to different blocks, like northern versus southern, or then have every site correlated due to some factor, some nested factors. Sort of similar to the model we did in week 2, and you could use that for a spatial model. People have done that. We talked about equal distance autoregression last week, and then we'll talk about unequal distance autoregression today. And to review, this equal distance autoregression involves just snapping all of the locations to pretend that they're all equally distanced, all have equal distance from one another. And then, we kind of derived very quickly sort of what's the correlation function as a function of distance under an exponential correlation function or a first order autoregressive process. And so we talked about it as a first order autoregressive process the same way we've been doing for time series models. And if you plot the correlation function, it looks like this sort of exponential correlation function. We can talk more about that in a bit. And if we do that, we were able to derive sort of the covariance function and write that out. I kind of proposed the inverse, the precision matrix for that correlation. And we also did a couple other ways of coding it in TMB. So that's what we've gotten through. But in reality, we might want to model the case where we have a bunch of sites that are distributed continuously across some domain, in this case, a one-dimensional domain from one part of the coastline to the other. And so if we have a bunch of locations, I'm assuming that we've ordered them as kind of sweeping north to south or south to north in order, so that we're looking at the distance of every one from the one that's upstream from it. Upstream meaning up in the one, in the ordered sense. The one that's. Am I making sense about ordering? I'm gonna Yeah. So if you've got a bunch of sites, I'm gonna be using the term upstream a lot because that's just sort of how I think about it. But I don't mean like streams on a network, on a stream or something. I just mean like a way of ordering it.
Jim, there's some markers over there.
Okay. So just before we get too far, I want to make sure that we're all on the same page. So like if we've got this coastline, maybe I'll try to, I don't know how to do this on a PowerPoint very quickly, but I'll be talking while I do it. So if you've got a coastline, so a line, and you've got different sites that are distributed along it, I'm just saying that you have to order it so that you go from one end of the line to the other and order it sequentially. And I'm just going to call upstream the low numbered and downstream the high numbered, so that like site 4 is downstream from site 3 and upstream from site 5 in the ordered numbering.
If you had more of a grid setup, how would you do that?
Yeah, so let's save that for next week's lecture, where we do this sort of equally spaced 2D model. So if we want to model unequal distances, and again, this I'm just kind of going to be doing this based on, we can talk about it more in a second. So the equation I'll put out here is similar to the equation we had before. So before we had epsilon at location s+1, has mean equal to the rho times epsilon at site S. So it's a first order autoregressive model here. And here I'm extending this first order autoregressive, but saying that the correlation rho is to the power of the distance between locations. And we'll see that that is identical to an exponential correlation function in a second, or I'll spend more time making that claim clear. And then the variance of this process is on the right-hand side of that normal distribution. And so that if distance equals 0, then rho to the 0 equals 1. So two sites would be perfectly correlated at distance 0. And on the right-hand side, rho to the 2D would be, rho to the 0 again. So 1 minus 1 would be 0, and so there'd be no variance on the right-hand side at a distance of 0, which makes sense. And also similarly, as distance goes to infinity, rho is assumed to be between 0 and 1 in this case. And so, rho to the infinity would go to 0, and the right-hand side, rho to the 2 times infinity would go to, yeah, exactly. Rho to the infinity would go to 0, rho to the 2 times infinity would go to 0. So 1 minus 0 would be 1. So the right-hand side would be the variance. And so as you go to infinite distance, it goes to the CIL, the geostatistical CIL of sigma squared. So that equation should make sense. If you just start plugging it, we know the two extremes make sense intuitively. I'm not going to try to derive it in terms of why there's a 2 in the exponent for the variance formula. But people can look it up if they want. And so the properties, again, the expectation, if you resampled from this process, the expected value is 0. The variance as distance goes to infinity is this sigma squared. The correlation between 2 points, is this rho to the d, and the covariance is the rho to the d times the pointwise variance, the same way it always is. So we could use that covariance to generate the whole covariance function for the spatial process. And just to look at it for a second more, we can do this change in variables where we say that we define a new parameter lambda. It would be the decorrelation rate. And if we say lambda equals the negative log of rho and plug it in, the first line is the equation we were just looking at. And the second line is plugging in for lambda, and here you can see that it's essentially an exponential correlation function. So that's sort of there's this one-to-one mapping of a first order autoregressive process. A first order autoregressive process is the same as an exponential correlation function for a correlated process. So like the first order autoregressive time series models we were doing, the like mean reverting, Kalman filter we were doing before was essentially like an exponential correlation function for a correlated process. That would be another way of describing the first order autoregressive models we were talking about before. Yeah, so the only reason I want to bring up this difference in parameterizations is to point out that this is an exponential covariance function. Yeah, so we can write out, we can do this. We can also describe this model instead of defining the probability of epsilon s plus 1 given epsilon and s, instead of defining the probabilities recursively by sweeping upstream to downstream, we could also define the joint probability of all of the random effects as a multivariate normal, with a covariance function equal this covariance that we derived. And so here I'm just writing out the covariance that we had listed as the bottom line previously. So that's the covariance. So essentially what we get to is, previously in the lecture, we had these sort of 4 different ways that we could have coded the model. And I thought about it later, and I think the lecture might have been, so there's 2 things I want to be talking about. One of them is separability, and the other one is how you can parameterize the same model in a bunch of different ways and get the same answer. And I think I was kind of mixing up those 2 objectives. But the goal of this is to show that, the real goal is to show that you could parameterize these models a bunch of different ways. And as Elizabeth, I think you were asking, aren't they all kind of theoretically separable, and because it's a property of the model, and it just wasn't able to detect separability in one of the cases.
Right.
And so yeah, exactly. So all of the models we're looking at both on Tuesday and today are separable models. And the purpose of it isn't so much to show separable versus non-separable, it's just to show the different ways we can parameterize it. And so again, that's the intent of today, is to show that we can parameterize this model these 2 different ways, and we'll look at the CPP code and again try to show that they give you essentially the same answer up to, well, I forget if they give the exact same to 6 decimal places, or whether I have a boundary issue that I didn't bother to. Okay, so let's turn to look at the TP code. Are there any questions about that material? I don't really have a ton of material today, except just to kind of go over these parameterizations, and then the exercises to kind of explore it in a bit more detail. So feel free to jump in with questions.
How often do boundary issues come up with these sorts of models?
I mean, it's hard to know. Like, what's that?
I guess that's very broad.
Yeah, I mean, I'm sure that I'm sure that people in a statistics department would be more careful about making sure that those boundary issues are not occurring. And the homework, all of the examples I've been doing, I've been trying to set up where I can kind of derive the equations as much as I can using sort of simple arguments. And so I'm not really getting into how to deal with boundary issues. So if you learn this in a stats department, I'm sure people would deal with those more. In terms of practical ways of dealing with a boundary issue, next week we'll be talking about this stochastic partial differential equation way of doing unequally spaced locations in 2 dimensions. And that has this sort of boundary issue that comes up in their models. And the way that they deal with it is by just making sure the boundaries are way past the location that you actually care about. So they'll just pad the location with a bunch of other random effects that have no data, that are kind of like predictive, kind of like the back and forth Nat and I had about how you can predict locations by just augmenting your random effects with a bunch of times with no data. You can do the same thing spatially, and then it makes sure that if you have a boundary effect, it's occurring in some place that you don't care about anyway. So that's sort of the general solution to boundary issues, is just to make the boundary occur some way past where you care about it. And we'll see, like I said, we'll see that come up again next week a bit. So, in this case, I'm simulating 100 locations, 1 through 100, indexed 1 through 100. I've got rho, which is the kind of decorrelation for a distance of 1. a marginal variance of 0.5 squared. And then I guess I'm gonna have 2 replicated samples per location and an intercept of 3. I simulate locations such that they're log normally have a log, the distance from sample S to S plus 1 going upstream to downstream is drawn from a log normal distribution with log mean of 0 and log standard deviation of 1. And then I simulate the random effect from the equation we were looking at before. So rho to the distance times the previous random effect value, and then a new random portion that's mean centered and with variance equal to this formula we were looking at, sigma squared times 1 minus rho to the 2 times the distance. So that's just taken from the formula in the slide. And then I simulate counts, replicated counts, 3 counts per site. And then down here we have the tag list of parameters. We compiled a model. We link it. The data we're giving it is, again, this options vec that tells it which method we're going to use on the C++ side, the matrix of data, and then unlike last week, we have to also tell it the locations. So that basically we have to tell it how far the sites are from one another. They're, after they've been ordered.
So that's just the distance between sites, right?
Yeah, distance
So,
from one site.
From 1 to 2, it's 5. From 2 to 3, it's 3.
Exactly. Yeah. Okay, so the locations are actually like the loc S from 1 to 100, the distance of site 1 from site 100 is 155 units, whatever the units are. So it's not like the distance from one site to the next site, it's the distance from site 1 to site N is the way I'm defining loc. And I'm simulating it. That makes sense, given the way I'm simulating it, where it's equal to the last one plus the different distance between the sites. So again, we'll just run this. We'll run both of them immediately, and we can already see that version 2, which is where we generate the covariance matrix by hand in the C++ code, took longer to run. So it took, in this case, about 10 times longer again. And again, if we check separability, we can see that version 2 failed to detect sparseness. So that the plot of the Hessian matrix for version 2 has a bunch of cells in the off diagonal that look like they're about 0, but it has only really matters this tri-diagonal pattern in the middle that version 0 also has. And you can confirm whether they're actually giving the same answer by just kind of inspecting them by eye. So looking at them again, all the off diagonals of the one that didn't detect sparseness very well are essentially machine limit are at 0, but it's just not correctly picking up that they're identically equal to 0. So the fact that this H2 is not correctly detecting sparseness is why it takes a lot longer to run. They do give identical answers to the, 6th or 8th decimal place. And looking on the C++ side, we've got the same general blocks of code that we're used to seeing. So we've got the read in the data, read in the parameters, do some basic bookkeeping, where we define the JNLL comp again for the different components, the negative log likelihood, retransform parameters, and then as we always do, we've got a block of code for the probability of random effects, a probability of the data given the random effects and fixed effects, and then the output reporting. The probability of data given random effects and fixed effects is, the same simple kind of thing that we've looked at over and over again, where you've got a dPLOS, in this case, the probability of the data given, in this case, a log-length linear predictor. And so again, the meat of the function is this block of code where we can move using namespace density down here because the namespace density isn't being used for this option 0. So option 0 is just using sort of elementary, functions that, loops and functions that exist in the base T and B, where it's saying that the first random effect is normally distributed with the marginal variance. So why would I be doing the marginal variance as the variance of that first random effect? Like this recursive equation is let's see, when we've been working out the code, we've been showing this probability of S for location S plus 1 given epsilon at location S. So we've been defining it recursively, but of course this recursive equation doesn't actually apply for the first location because it has no location upstream from it. So I'm being kind of lazy about it. And you could call that like a boundary condition. Again, I'm not putting in the equation, there's a missing equation that's implicitly there that defines the probability of the first random effect that's the most upstream random effect. And why would I want it to have a variance of sigma squared in this case? Sorry, I should have thought about this more before I used the notation I did for the slides versus the code. So I'm going to redefine this first equation this way. So okay, so let's break this down a little bit. I'm kind of going through a couple pieces at once here. So if we've got this equation for the distribution of epsilon at S plus 1 given epsilon at location S. If you go an infinite distance, what's the variance for epsilon S plus 1,000 given epsilon at location S?
It's going to be just sigma squared.
Yeah, it's going to be sigma squared. And why is that?
The little 1 minus rho squared. Just
Yeah,
to zero.
it'll
Goes to
go,
one.
exactly, yeah, so, I mean, the way I would say it is that, you know, we've got a conversion power series, where, you know, the variance is accumulating as a sum as you go from location s plus 1 to s plus 2 plus s plus 3 plus s plus 4. And that can, you know, so s plus 1 given s, the variance that remains is rho times the variance. S plus 2, it's rho times the variance squared. S plus 3, it's, you know, the variance times rho cubed that remains after going 3 distances. And so if you sum across all of those, that's a conversion power series as long as rho is between -1 and 1. And the value it converges on is this variance, the variance of the conditional process divided by 1 minus rho squared, and that cancels with this. So the marginal variance of this process is sigma squared, sigma epsilon squared. And so in the code, we're going to define the first location, the one that we aren't modeling anything upstream from. We're going to define it as having variance equal to the marginal variance of the process. The variance, if you imagined that you had also modeled a bunch of ones upstream from that, what would the variance be if you know, of that whole process?
Sarah,
Did that make sense? That we could say it a couple other ways.
yeah, can we say it another way?
So, yeah, so another way is we talked about how a correlation function looks like this, an exponential correlation function. And we talked about how we're not really going to talk about like the sill and the nugget in this class very much, but the semi-variance function for that exponential correlation function looks like this, where it accumulates, you know, it goes to an asymptote. And the asymptote of that is sigma squared. And so, so if that doesn't make it clear, I don't know. But yeah, so the point is that, you know, if you've got a bunch of locations along a stream, that you're modeling, and you know, you're saying that this stream, given this stream, has the variance is this, and so forth, but you still need to figure out what's the variance the first stream that you're sweeping down from. You might want to say that the variance that stream is what would occur if you modeled it conditional on a point that was like kind of infinitely far away. And so you would kind of, in your head, you'd imagine that you've got some stream up here and that you've actually walked the length of that stream and seen how much variance accumulated up to that, and that's the stationary, you know, that's the marginal variance of the process, which is equal to sigma squared. So you want to start, you know, if you're doing it this upstream to downstream way, if you're defining the probabilities conditionally, you know, recursively, you still need to define the variance, the first that you sweep down from, and you probably want to define that as having the variance equal to the marginal variance of the whole process.
Is the marginal variance the same thing as the sill?
Yeah, in this case, it's the sill. I'm being yeah, sure.
Okay.
So like, I'm just sort of like thinking about the time series, one-dimensional time series and a one-dimensional spatial model. That's not actually a stream because presumably like events that happen in the present don't affect events that happen in the past. But spatially you have that
Yeah.
both directions.
Well, exactly. So, okay, so that's interesting. So, the short answer is that these models do not distinguish in any way between spatial and temporal. We're using the exact same models for space and time. And that's interesting because, of course, in time, there's this sort of causal, we all know, I mean, or it's sort of an axiom of how we interpret the world that things don't cause things prior to them. And so there's a lot of interesting causal statistics coming out about how to decompose a joint process into a bunch of conditional statements, and how to interpret that directed acyclic graph of decomposing it that way as sort of a causal model. And you can use that directed acyclic graph to work out causal statistics. That's sort of like Judea Pearl does that, and then there's sort of a synthesis of Pearl and Rubin that people are calling like targeted maximum likelihood, and it's totally abstruse, and I can't make heads or tails. Yeah, the simple answer is that in all of our models, there's no difference between how we're dealing with space and time. If you wanted to take these spatial models and convert them to a causal statistics where you define sort of causally what's causing what, then you would take your time series model, you decompose it where t causes t plus 1, and if that causal assumption is correct, you could start making causal inference. And similarly, you could also do that on a stream network if you knew that like things upstream cause downstream, but they don't cause upstream or something. But the point of causal statistics is that it is only valid if you correctly, a priori, decompose what causes what correctly. So in those statistics, it also doesn't really matter if it's space or time, as long as you just correctly decompose what causes what.
But the correlation is still going to be symmetric.
Right. That's
Yeah.
the kind of way you have to look at it.
Exactly. And
Yeah.
exactly. And so for a stream network, for instance, in time, it makes I always start with time because it's sort of more intuitive for people to think about sweeping upstream to downstream in time. You know, people always want to go, what's the probability of t plus 1 given on t? In space, if you have a stream, you could sweep upstream to downstream, or you could equally validly sweep downstream to upstream, and the math would be the same. And the reason is that, as John says, you know, the correlation matrix that it ends up generating is symmetric either way, as I guess we can see in the code in a bit. Well, as we already saw. So in this case, H0 is decomposing, or the method, method 0 is sweeping from, sweeping upstream to downstream. It's sweeping from site 1 to site 100. And it's defining, site 2 given site 1, site 3 given site 2, but it's still internally working out that the resulting correlation matrix and Hessian matrix are symmetric. And if you, kind of naively, you'd think, oh, well, it's really only defining site 2 given site 1 and site 3 given site 2, and so you might wonder, oh, well, where's the part above the diagonal even coming from? Because that's not what we're at, But it's internally, it's still always generating a symmetric covariance matrix.
What's going on with cell 3,3 between the two matrices? It's 1.821, or the one to the right of that.
Oh,
It's got a
18.
oh yeah.
Oh,
and then
I see
plus.
that. Oh, my bad.
Yeah. Yeah, so, okay, so this one, we start out the process at the marginal variance, and then in this case, the variance of location pass given location S minus 1, the additional process error that accumulates is less than or equal to sigma squared, where it's less. I mean, it becomes sigma squared at an infinite distance. And that's all you have to do to solve, to define. And this goes back to sort of the ways that I think about sort of the fundamental laws of probability that undergird this whole approach, is that you can either define, the joint probability of all of the random effects, or you can decompose that into a series of conditional probability statements where you can define the probability of site 1 and site 2 given site 1 and site 3 given site 1 and 2 and site 4 given site 1, 2, 3, and so on. You can always decompose any joint probability that way. And that's the law of the axiom of conditional probability is what I call it. But in this particular model, because it's first order autoregressive, we only ever need to define site 2 given site 1 and site 3 given site 2 and site 4 given site 3. We don't have to do site 4 given site 3, 1, 2, 3, 2, and 1. We can just do it site 4 given site 3. That's what the first order autoregressive means, that it's first order Markov. Okay, well, maybe we're kind of getting into a lot of tangents here. I'm getting into a lot of tangents here. So the other approach that works, that I knew how to implement when I set this up originally, was to populate the whole covariance matrix, so cov SS, which is this whole square, dense square matrix, and then plugging it into this MV norm statement. So what do we know about MV norm in caps lock?
You mean zero multivariate normal?
Yeah, so it's a mean multivariate normal. Like, where does it come from? Like, how do we use it in the code?
The density.
Yeah, so it lives in that namespace density that ships with T and B. So T and B is using C++. C++ is kind of like R, where you have kind of a base distribution, and then you can also use additional packages. And so T and B, when you download it, ships with this namespace density. You can confirm that it's part of T and B by doing that. Remind me what the URL is for the Doxgen documentation these days. Does anybody know?
Yeah, it's casker.github.io /@conf. There's a module.
Go down.
So you can kind of confirm that it's part of MV norm, part of TMB, because it shows up in the Doxgen documentation. In this case, it's pretty confusing because it just skips right to, it says MV norm and then only defines MV norm T as the output object of the function MV norm, where you input a sigma matrix, and C++ has this matching based on object types. So if this bool use atomic equals true means that use atomic is true by default, and if you don't include a boolean, it doesn't. It just uses the default. Positive definite covariance matrix with this format. So this is sort of matching the format that we're using in the code. And as we said, the one other thing to remember about these namespace density objects is that they return the negative log likelihood. Which is kind of annoying that they don't list that. They don't say that in the Doxgen documentation. But
Wait, can you open that again? I'm just trying to understand where it's evaluated by the perfects.
wait, say it again.
So the MV norm is sigma and then close parentheses and then it has the X.
Yeah, totally.
And so what is it doing with that?
Yeah, it's funny, the way these constructors are working are very weird. And so you could call MV norm and not have it. So if you do MV norm sigma by itself,
Yeah.
it returns an object that's a function. And so if you do MV norm sigma and then and then a parenthesis again in X, it makes this object that defines a function, and then it immediately evaluates that function with respect to X. And X is the vector of random effects that you're evaluating to get the negative log likelihood of.
Okay.
But I think the way they did that is because Casper sometimes, and I've used this in my code, it's kind of useful, but it's complicated to explain and hard to read for people that are not used to it, where MV norm sigma that constructs this object that defines a function, you might want to just save that and then use it later in your code. And so if you save it as an object, you can use it on multiple random effects without constructing it over and over again. So that's why I think why it has a different format than like we're used to seeing in R, where you would think, by default, we're probably used to thinking MV norm should be a function with two inputs, one sigma and one X. Whereas it's actually MV norm is a function that returns a function that then you have to evaluate again on X. So in the code, that's why it looks like this, where you've got MV norm, you pass it your covariance matrix, and then you pass that another vector in this case, where epsilon s has to be the same length as the dimensions of the square matrix covariance, cov SS. Anything more to talk about in this block of code here? Or, sorry, in this block of code that we're.
So sort of the takeaway in terms of sort of time of processing, that if you do it by a recursive strategy or using the built-in functions, it's generally pretty fast, but then defining the whole covariance matrix by hand is like not fast.
Totally, exactly, yeah. Cool. And
Wait, but don't you use a recursive strategy in the first one and define the whole covariance matrix in the second one?
exactly, yeah. So both of. Wait. So say it again, Nat. And
So the recursive strategy is fast, and the defining the whole covariance matrix is not.
yeah, and the reason for that specifically is that TMB, for whatever reason, using the MV norm, does not correctly identify the sparseness of the Hessian. So I don't think it's the assembling the covariance matrix itself. I think the reason that it goes about 10 times slower is because, the method 0 correctly detects the sparseness and drops a bunch of locations in this Hessian matrix when doing the calculation. Whereas the other one, for whatever reason, doesn't recognize that 1 septillion is essentially 0.
You build a function that just went through the covariance matrix and set anything below some limit to 0.
Well, but this isn't the covariance matrix, this is the Hessian that it's detecting internally. I mean, Casper, presumably there's some. I don't really want to get into the architecture of how TMB is detecting sparseness because frankly, it's not something I even fully understand.
Gotcha.
Yeah. Okay. So, any other questions about the code for now? So if not, so I should really edit this. Cast it correctly, text structure. Yeah, so, okay, and then the other lesson that I didn't really stress as we were going along, but this unequal, I mean, and it just makes sense intuitively that this unequal distance version generalizes the equal distance version. So if every distance was equal to 1, if every distance going upstream to downstream was equal to 1, then this would be rho to the 1, or rho times epsilon, and this would be rho to the 2 times 1, or rho 1 minus rho squared times the marginal variance, which is, once I decided I cared, what I edited this original equal distance autoregression to look like. So the unequal distance is perfect, perfect generalization of the equal distance, which is what would make sense. And what I'd like to do as an exercise is have people go in and edit version 2 to use a different function besides the exponential correlation covariance function. So instead of this line where you say that the covariance equals sigma, the sigma, the CIL times a exponential covariance function, replace this function with some other covariance function that you could look up on Wikipedia, and try that one again, and we'll look as a group at the resulting Hessian matrix. So that'll be the exercise. Maybe we take a break first. Do people want to take a 5-minute break? Okay, so let's plan to come back at 10:05, and then we can work on the exercise.
Jeff, did you say you're moving to Alaska?
But let's break out into the exercise first, and then I'll come back and ask you the question. Okay, so like I said, so now let's just go right into the exercise and take a few minutes to do it, and maybe we'll finish the class a little early today. If you don't have a so let's go back to, I think I said it in slide 1, although I might have stripped it out a bit. So TMB uses automatic differentiation to calculate all the derivatives, and so what implications does that have for coding in TMB?
The type thing?
Well, there's the type thing for sure, but there's kind of more of a fundamental constraint that implies.
Anything that can't be derived can't be put in there, I guess.
Yeah, they're differentiated, you mean?
Yeah, differentiated.
Exactly, yeah. Yeah, so all of the functions you use in TMB have to be differentiable. The process, the function relating the joint negative log likelihood to your parameters has to be differentiable everywhere. And technically what it's doing is, if you have a non-differentiable function in there and you figure out how to trick it into the compiler not realizing that, the compiler's smart enough to try to notice if you're doing something dumb and have a non-differentiable function. But if you can trick it into still allowing you to do it, what it'll do is, depending on the starting values, it'll just define whether you're in one differentiable subset or another, and it will assemble the graph representing the model based on the conditions in that area. And so you can end up with models that you think are right, but are not working correctly because it's only doing, it works out the graph representing the dependence of your joint negative log likelihood on your parameters, conditional on where you start it. And then if you have an if-then statement or something else that's not differentiable, once you cross that boundary, it might not correctly work out what's happening to calculate the likelihood in that new area. So that's the reason you never want to have a non-differentiable function like an if-then statement in a TMB code or a TMB. Okay, so the reason I bring that up is that have you ever, has anybody found a good Wikipedia page summarizing different correlation functions? I'm trying to think. There's got to be some place that lists them, but if you don't have, you know, like what are the correlation functions we talked about a couple of weeks ago? We listed a few in a slide a couple of weeks ago. And Jay also brought them up when he summarized J Verhoef's. Oh, we didn't do the intro this week, so we can do the intro of it. Does anybody, I mean, I'm sure some of you guys do, but what are some of the correlation functions that, like Jay talked about in J Verhoef's paper in week 3?
Oh, like what was that, like bouncy one?
Yeah, there was like the whole function or something. Yeah. And what were the other ones?
There was the exponential Gaussian.
Yeah, those are Matern, spherical. Sometimes he uses linear, which is like, the linear looks like just goes down and then hits 0 and stays at 0 past that. Or spherical looks like something like that, and hits 0 and then goes to 0. And the point is that the spherical and the linear are not differentiable because the function, like the linear, has a negative slope, and then it hits 0, and then if this hinge becomes equal to 0, and so that function is not differentiable at the point where it hits 0. So where I'm going with this is you can use any correlation function you want for the exercise, but do not use the linear or the spherical because those are not differentiable. So I recommend for most people that you just use the Gaussian correlation function if you don't have some strong. So okay, so people will code that up and come back at 12:25.
12?
10:25. Yeah.
10:13 now.
And if you get it done, maybe try to install GoToMeeting or whatever so that we can have you plug in your screen. Okay, so Arno, what was your question again? You were asking why we relate sites to sites that are 10 times k units apart in loc x. And I'm confused because there's no units defined in loc s, and I'm not sure what you mean by k. Well, feel free to rephrase the question if you want. If there's still something you're confused about. And Kristen, did you have a question?
Yeah, okay.
That one was the easy.
Yeah, so you don't do the linear.
if you used a linear, wouldn't just all of the distances x far away not be the same? Like the likelihood wouldn't be dependent on the
Yes.
rest of it, so you basically just have two separate space units.
Well, so, but if it's, so in our, if you had a linear and a stream, sites, and you have a linear correlation function. Jesus. I should have been. So in this case, like, this site would be probably too far enough away that the correlation from this site to this site is 0, but still this site, the correlation from this site to this site is 1, or non-zero. So I guess maybe the linear is reaching 0 such that only these two sites are correlated and all the other sites are uncorrelated, just kind of eyeballing it. But if you increased it, that now maybe this site's correlated with this site,
Which site? Oh, there it is.
this site to this site.
Can you circle it? I'm sorry, I can't see
Maybe
your mouse,
site,
Jim.
maybe site 1 and 2 are correlated, but 1 is not correlated with but 1's not correlated with 4. I never use the linear, so I'm confused about how it actually works.
No, I don't know that anyone uses, a linear doesn't work in 2D, it only works in 1D.
Okay, yeah.
And I don't think I've ever seen it used.
Yeah, and I'm actually even getting confused explaining it, because here it looks like maybe site 1 and 2 would be correlated, and site 2 and 3 would be correlated, but site 1 would not be correlated with 3.
Yeah, this is pretty, I mean, there are a few covariance functions that have a closed support.
Yeah.
So they go to exactly 0 at some distance.
Right.
Yeah.
So,
Yeah, like linear and spherical are those that go to exactly 0.
so there are, and that's nice because you can actually get a sparse covariance matrix potentially.
Yeah.
Depending on everything. But
Although I don't know why that's useful.
if you're in covariance land and want
Yeah.
and it's like you're over large enough
Yeah.
domain that
Yeah.
a lot of your things aren't correlated at all,
Yeah.
then you can leverage that.
Yeah.
I think, and before you can get it,
Yeah.
so you can get sparseness without going to the Hessian. And
Yeah.
Because defining, before the SPD approach, defining some sort of Markov.
Well, but I guess I always get confused about why the sparse correlation would be useful, because to calculate the joint probability, you'd still need to invert it anyway.
Yeah,
But I guess you could do like the Cholesky would be easier,
Yeah.
and you could do some.
the Cholesky goes from n cubed to n,
Yeah.
so the 3f's.
Yeah. And so in that case, like, I guess if you're doing like some basis function approach to spatial correlations is easier or something. I don't know.
But, so your log likelihood would be not differentiable with respect to your range parameter.
Yeah, exactly.
But otherwise, but if you weren't fitting the range parameter for some reason,
Yeah.
you could still use one of these limited support.
Yeah. So maybe one takeaway from this discussion for people that are not following the details is that there's a lot of different ways that people derive spatial models, and you could spend a lifetime kind of trying to work it out. I just teach sort of a particular strategy that sort of covers the full span of questions, spatial temporal questions, using sort of a small subset of tools that are out there, but there's a lot of other tools people have come up with for doing this. Anyway, I forget what the original point was, but.
Trying to understand the linear function.
Yeah. Yeah.
Yeah, this Yeah. Right, so this is the room of noise. And so this, well, that's so that's where it goes from 0 to 1, and then depending on how far away you are, that correlation in noise varies.
No, for your transformation of this thing or something. This is me, cool. Walk that one out. Yeah, alright. So, all I did for this one.
Could you make yours a little bigger, please? Do you need it?
Yeah, of course. Is that good?
Yeah.
Alright. So all I did was pretty much copy option 2. And then, I'll just do it over again.
Well,
Or-
yeah.
Sure.
No, yeah, go for it, whatever you want to do.
Yeah, so I just pretty much copied all of section 2, and then made a new parameter called kappa, and then made legit row a parameter vector rather than a parameter, and made row legit row, comma 0, or parentheses 0, and kappa as the exponent of legit row 0 or 1, and then changed this sigma times power bit to the return of the distance, and then rho and kappa,
Totally.
and that was it.
And so you ran it, and you got just display in your terminal down below or your console. The opt. So now logit row, it has length 2. The first value, which I guess is I forget the Materin parameterization that it's using offhand. I mean, does anybody remember the first one was called? The first one I think is like the
That's the range parameter.
Yeah, and what a range parameter of 18.6 means, I have no idea.
Depends on how they characterize it internally.
Yeah, exactly, and I just don't remember, but it seems like the final gradients seem to indicate that it's still working okay. Sometimes at 18, it kind of scares me because if you're working in log space, that seems like a really high value, but I assume it's working for now. Well, except looking at the standard error, the logit row for that 18, the standard error is 5,000. So the CV, so it's probably logit row. That first parameter is probably going off into La La Land where it has no information. It's probably kind of essentially hitting a bound where it's sort of turning off some, the function is kind of getting infinitely steep or something.
I expect it's having problems fitting the logit transformation of that.
Oh, sure, of course that's what it's doing.
Like it's going to 18, which means it's
Of course, because it's logit transformed. So maybe you could grant, maybe while we're talking about this, well, maybe in a second we could change that row from a logit to a log, like a log transform.
Parameters just have to be positive.
Yeah, I think so. Yeah. If it's the sort of standard Materin parameterization. But while Grant's doing that, we can also see that we checked the sparseness of the matrix. Grant, are you willing, while you're doing that, just on the terminal, just write out the Hessian matrix and extract the first 8 rows and 8 columns of it? And so what part of the point of this exercise that I wanted to do was to say that if you put in a Materin or some other correlation function, it's no longer first order Markov. So the exponential function, we saw that this first order autoregression is kind of how we were talking about it. We were talking about it as like a first order autoregressive process where next year is equal, the expectation for next year is equal to this year times a row parameter. That's kind of how we started talking about it in the time series land. And then today I tried to show that you could reparameterize it to have it look like an exponential function. That because it's first order autoregressive, as John brought up early in the class, it's also first order Markov. And so we kind of know that the partial correlation of one site and the next site is non-zero, but if the sites are not adjacent to each other, the partial correlation is 0, conditional on the sites between them. So that's why the Hessian is sparse for the first order autoregressive model. But if we put in a different covariance function, then this Hessian is definitely not sparse. It's not just incorrectly detecting sparseness. But all of these are non-zero. Some of them are really non-zero, and some of them are kind of close-ish to 0. But this isn't like a machine tolerance difference from 0, like 10 to the negative 17. It's actually an important non-zero, probably. And so, what that shows is that the Materin correlation function in this case is not. It's the Hessian for that Materin correlation function is not sparse.
Do Do we know that empirically from looking at the equations for the model?
I'm just looking at the equation for the Materin, I wouldn't know that. Yeah, so this is sort of stuff that, this is sort of the toolbox that I've gotten used to. You know, this is sort of like learning the special cases. It's the best way I know how to do this. But I guess when I'm in doubt, I always try to run a numerical experiment. And so one numerical experiment you could do if you get a new correlation function. Let's say you look up the correlation function for a second order, like an AR2 process. And you know theoretically that it's second order Markov, but say you're not positive, you're like, oh, I think that's probably second order Markov, but I'm not sure. You could run a numerical experiment where you put in the correlation function for a second, for a second order Markov, for a second order autoregressive process. Put that in, run the model, and look at the Hessian and see if the Hessian looks like it's sparse or not. And if it looks sparse, I would take that as evidence that your intuition had been right. Like, not being a trained mathematician, I guess I find those sort of numerical experiments to be pretty helpful to kind of make sure that my intuition's right. So it looks,
I fixed it now.
You did, okay.
Compiling it.
Okay. Was that, okay, so maybe for now well, I wouldn't want to miss any of the excitement of watching it compile, so maybe I'll just wait until it's done. Is it still compiling on is that what it does on your machine when it's?
Yeah, but it's a good sign if it hasn't bugged out by now. There we go.
So it's a good sign that all the U steps are at 1, so that means that it's not like the inner optimizer is still kind of close to quadratic for all of the inner optimization steps that it's doing.
So you're saying if it goes off to some big number, or the value or the?
Yeah, the value after that it says U step.
Oh.
Where it's saying U step 1. That value, as we mentioned briefly, what that U step is doing is the inner optimizer is doing a Newton optimizer, where the distance it goes depends on its estimate of the curvature of the inner likelihood. And that Newton step will get really bad if that inner likelihood is not quadratic. And so the U step is basically this kludge they built in where they do smaller steps if they detected that the inner likelihood is far from quadratic. And so that essentially what that means is U step for a well-behaved model will stay close to 1. And if it gets away from 1, it means it's struggling. And your model, sometimes when your model crashes, if you look at it, it's when the last time it did the inner optimizer, that U step just got lower and lower and lower until it got to like 10 to the negative 16 or something, and then it moves up.
This seems more reasonable.
Yeah, okay, so this is good. So the logit 1, now that it's not in logit space, but in log space, it's exponentiating 1.296. Which is a value greater than 1, which is why when it was in logit space, it was just trying to get as close to 1 as it could. And then the second one is less than 0.59. So I'm trying to remember. I think that an exponential correlation function is equal to a Materin function in 1 dimension with smoothness of 0.5. So I think. And this is another just kind of like special case that nobody would have any reason to need to memorize for this class, the basic purpose of this class. But I think the correct value should be for logit row, the second slot should be the log of 0.5, and it's close to that, so that's kind of nice. And we'll talk more about the Materin function starting next week, where we use it more. Okay, and then can you look at the Hessian again? Can you generate the Hessian? Okay. So in this case, again, the Hessian for the Materin function is everywhere is pretty far away from 0. So this Hessian, this Materin function is not even close to being sparse for the inner likelihood, for the inner optimizer. And so if you look at how long this model took to run, it probably was closer, it was probably pretty slow relative to the exponential, relative to version 0 before, which detected sparseness. So I wanted to do this as an exercise, in part in response to your question, Elizabeth, from last class about when would a model stop being sparse? One way to do that is to have a different correlation function that's not by nature sparse. So did anybody else get it working, or did anybody else have an experience that they want to share, like a problem they want to share?
What I was trying to figure out was, once you have the new correlation matrix that you're working against, how would you simulate that data?
Yeah.
Because I can figure out the correlation function, but then turning that into, like, given S, E of S minus 1, turning that into E of S.
Yeah, so one way to do it that we've seen in the class already, you remember I think it was in week 3 when we talked about generating data from a multivariate normal. And so do you remember how we did that? How we generated data from a multivariate normal?
Well, in that case,
Or
we just
anything.
broke it down into little bits and then our norm did.
Well, so that was one way we did it in that week was yeah, exactly. And so how did we break it down into little bits? Like, what did we do to the covariance? Well, go ahead, Don. I mean,
It's Cholesky.
yeah. So that was the trick. So like we were talking about. So there's sort of like two main ways I ever think about a covariance matrix. One of them is the eigen decomposition, and the other one's the Cholesky decomposition. And if you have a target covariance matrix, you can either use the multivariate norm. You can always just assemble the covariance matrix and use the dmv norm function in R to just generate all of the random effects jointly. But if you didn't want to use a canned package in R, you could assemble it by hand and then do the Cholesky decomposition and then generate just a vector of IID standard normals and multiply it by that Cholesky matrix, and that transformed vector would have covariance equal to the matrix you wanted.
Okay.
Yeah. So that would be the easiest way to do it. Are people do people have enough? Is that enough information for people? There's sort of more kind of theoretical interpretation of the Cholesky if people were not maxed out on kind of computational trivia for one day. Let's hear it.
Yeah.
Okay. So I mean, we've been talking about how like a lot of models you can sort of think about jointly or collectively, jointly or conditionally. So if you have a vector of random effects epsilon of length 10, you could have all of epsilon be multivariate normal. and that's kind of the joint probability of them. Or you can have epsilon be a bunch of IID standard normals and multiply it by the Cholesky, and that's sort of just a computational trick for doing sort of the same thing, where you're generating a bunch of. Oh yeah. Does anybody know how to?
Oh, you're on it.
Am I?
I stopped sharing.
Well, but you're still listed as the presenter.
No, I'm done.
Dismiss Grant Adams as the. Wow. Okay, and then I don't know how to get rid of this thing. Oh, I have to share my screen again. Okay. So one trick is the doing the multivariate normal in R using DMV norm. Another trick is take your target covariance matrix, take the Cholesky, generate a bunch of IID standard normals, and multiply it by the Cholesky. And that's sort of similar because if you do that, you have to generate all of them at the same time. But the Cholesky is, so let's say the other way to do it is to do delta. Delta is IID. Jesus, I really gotta find the drawing pad that I had last time. And then say that epsilon equals the Cholesky decomposition, which I call L for lower, times the vector delta. The Cholesky, the structure of the Cholesky as being lower triangle means that, it's a vector, it's a matrix where all of this is zeros, and it has the diagonal, and then the next one, and so forth. And so the Cholesky, you can kind of see, the first element of epsilon is just equal to delta times the delta times the upper triangular, the 1, 1 element of the Cholesky matrix. The second element of epsilon is equal to delta times the second row, which has 2 non-zero elements. And then the third row of the Cholesky has 3 non-zero elements. And so the Cholesky, in some sense, encodes sort of the conditional, the way of representing epsilon as a recursive equation. So the elements that Cholesky are internally, algebraically, are the linear algebra solution for how to recursively decompose the elements of epsilon into a bunch of, represent the elements of epsilon on the other elements, the prior elements of epsilon. Like the second element of epsilon is equal to the effect of the first element of epsilon plus a new thing. The third element of epsilon depends on the first element of epsilon and the second element of epsilon. And so if you do, and that's sort of the same operation we were doing under the axiom of conditional probability, where we decompose the joint probability into the probability of the first element, the probability of the second given the first, the probability of the third given the first and second. And so there's sort of like a fundamental mapping of the order of operations for the Cholesky decomposition and the way that we decompose a joint probability and a bunch of conditional probabilities. That's all I really want to get to. So if that made any kind of intuitive aha moment, then go with it. If it didn't make sense, then you can ignore that tangent. So like a lot of what people used to do by hand in geostatistics, people have eventually realized it's just linear algebra that you can do like with standard linear algebra operations, like the Cholesky matrix. Okay, so that was all the material I wanted to cover. I had a little bit of extra material that we already started talking about in the kind of back and forth that I'm attributing to Nat. Sorry to be that you're famous for our back and forth for this, but so sometimes people want to know, how do you, if you extrapolate density from a spatial model to some new location, then well, if you have it, like under our kind of nested site model, site as random effect model, it's really easy to predict into a new site because it's just normally distributed in IID with the sites that you modeled already. And so if you do that, and you wanted to calculate total abundance across all those sites, you can just calculate the abundance at the sites you modeled and the abundance at the sites that you didn't and sum across them. So like in the forecasting, if you wanted to calculate what's the average abundance from year 1 to 120, you could just take the average, sum the abundance in every year and divide by 120. If you're doing finite sampling stuff, this is the only time I'll talk about finite sampling in the class, but sometimes in finite sampling, you actually perfectly observe the value at some subset of sites. So like you might have a village of 100 people and you sampled 20 of them for a disease and you know exactly if they have the disease or not. You want to figure out what's the predicted incidence of that disease for the whole village. Well, the ones you measured are not random variables, so you just calculate the known data and add that to the predicted disease probability for the unsampled individuals. And that would be like the finite population prediction for that problem. But it's harder to do all those calculations when your random effects are highly correlated, like in a spatial model, in which case, the predicting to the new sites is correlated with the sites that you estimated, and they're correlated with one another, and so forth. And so basically, my advice in all of this is just let TMB work it out with the delta method. Well, or you could do a posterior sample if you wanted to get away from the Taylor series assumptions that underlie the delta method. But usually nobody really cares about that level of detail, in my experience, in anything I've ever done. And so usually the best way to calculate the predictive, the standard error or the predicted variance for some derived quantity is just to calculate it internally to TMB, including how it depends on random effects for sites you have data for, and random effects that maybe you don't have any data for, and it depends on the parameters that you're estimating and have some variance, some standard error. Just do that calculation internally, and TMB will use the delta method to propagate the variance of your parameters and the variance of your random effects, and give you a predicted variance that has good coverage properties, as long as the model is correctly specified. So that's sort of my little note on extrapolating and calculating derived quantities in a spatial model. Okay, so that's all I wanted to cover. Does anybody have any last questions? I think these Thursdays are kind of long, so hopefully people aren't too.
Could you show us an example of the extrapolation?
How about?
That's like the forecasting we do?
Yeah, totally. Well, like the forecasting is extrapolating in time.
Mm-hmm.
And so if you were interested, you could do like in that homework, homework 3 extrapolated 5 years, you could ask what's the average density across all 36 years. And that would, include, if you calculate that internally, it would include, and then calculate the standard error of that internal calculation. That would propagate the variance of years 1 through 31 that have lower variance because you have data associated with those years, plus the greater predicted variance of years 32 through 36, where 36 has greater variance because it's propagating, it's extrapolating forward in time further, and the delta method would just properly account for all of the variances and covariances of that calculation, which would otherwise be pretty tedious.
Gotcha.
Yeah.
So how we did it in the homework. Wrong.
What's that?
Was wrong in a way.
Well, I haven't graded the homework yet. I think that,
did. Homework was wrong.
okay, yeah, I mean, I think that, yeah, I mean, I forget what coverage probabilities people were getting. I didn't ask people to calculate the total abundance across all years, but hypothetically, if you'd added that in and calculate the standard error of that internally, you'd probably get a metric that has good coverage.
Gotcha.
I think somebody asked me to do that last year too, and so I did, I have a piece of code sitting around where I did that, where I just took the same model and added in a block of additional code where I calculate total abundance as the sum of abundance, the sum of the linear predictors for every site, and then I just A/B report out that total abundance. And that would be the way to get a standard error for the prediction of total abundance across all the sites that properly accounts for the variances and covariances of all the random effects. And incidentally, it has an issue called retransformation bias that I think we'll talk about next week. Any last questions?